live.
Great. Okay. Welcome everyone to another project presentation. Today we have Lev, who is going to be talking about the motion and special relativity in Wolfram models. So this is a very exciting, interesting discussion, and this is a project that Lev actually did during the summer school. So with that, Nick Dugan will be joining us, and Lev, please tell us about your project and share your screen when you're ready.
Yep. Thank you, James. All right. So, my project is in the direction which I think is the most important now to narrow down the space of the possible Wolfram models that can represent our universe and our space-time and our particles and the interactions that we have. And what we need to do for that is we need to look at the models, try to understand what kinds of things correspond to the observables we have in the real world, and what kinds of conditions we need to have in order for those observables to behave the way they're supposed to behave. And so my previous project was actually also on that topic. I explored how the hypergraphs can be structured in order to have the symmetries that we have in our space. There the idea was that we need to have translational and rotational symmetries, and it's not very trivial to get that with hypergraphs, but it's possible. And well, actually, I guess the peak of this approach is the part from the original technical introduction where energy and momentum are defined as the flows of hyper edges through space-like and time-like hypersurfaces in the causal graph, because that's a very simple and kind of intuitive definition that doesn't rely on the specific rules we have, that doesn't rely on our definition of particles or something like that. It's just something that you can define in a very, very abstract way, and then instantly get some useful properties. For one, they behave intuitively, that the particle that's standing is it has some energy but no momentum, and then once it starts moving, you get the right transformations of energy and momentum, and then if you transform the causal graph under special relativity, then the energy and momentum transform the way we expect. However, it is still unclear whether the actual kinematics of what's going on inside the system are going to transform the right way if we apply the Lorentz transformation. So in this project, what I do is I investigate that by defining what a Lorentz transformation is here, and I define a very small Lorentzian boost, and then I check some systems for whether that boost behaves the way it's supposed to. And so, first of all, just to get an understanding of what the problem is, let's look at an example where it doesn't transform the way you expect. So if you have something like, first of all, just to have some toy systems you will be working with, here are the models for a one-dimensional space with a particle and the clock, and then the same for the two-dimensional space. And so here, the particle is constructed in this way that I have this, so it has the main point at which it is located, and then it has this little tip that indicates the direction of movement for the particle. And as we will see, this particle is actually a photon. And so, yeah, and here is the clock, and the clock just grows rings around itself, and that's how it counts time.
Sorry,
And
Liv,
so
can we
if you,
do one thing? Are you able to zoom in a couple notches? Just for
yes,
you. Oh, that's a lot. Okay.
mm,
Great. Okay. Looks good. Thank you.
yeah. So if you run this simulation with the one-way model, then we will see that the particle is moving and then the clock is standing. And yeah, so here is the result of the simulation. We can see that the particle is just moving. So far it's nothing very complicated, but then the problem is, what should we do to this system to transform to another reference frame? So if this particle were moving with some finite speed, then there should be a way to get a system that's equivalent to this one, but in which the particle is actually standing. So, it has some speed v, and if v is not equal to the speed of light, then we just move to, we pass to a reference frame that moves with the speed v relative to the original one, and the particle is standing. However, if you look here, we see that no matter what we do to the system, since we have this rule for the movement, if the particle looks like this, it is always just going to move in the direction that the tip indicates. And what the Lorentz boost is supposed to be represented by in the causal graph is this system of tilted variations, and we are supposed to say, okay, so the events that happened above this line, the events that are above this line, they have happened, and we apply them sort of like you would apply git commits. And then we start, we take the system which we obtain after applying the events to the initial state, and we evolve that system. So if you look at that, okay, that's a bit blurry, but if you look at that particular system where we have the particle and the clock, we get the causal graph, and then we can slice it, and hold on, there. Yeah, so here's an illustration for how we slice the system.
Can you just to roll back a little bit in more detail, explain what actually happens to that graph? So what is this particle? How is it moving? Why is it reflecting? What the actual events are? Just just slow down.
Yeah. So again, the particle is what's highlighted here in red and here in red, and it's this little sum graph. So we can see that the space is this basic grid, and then if there's nothing overlaid on top of that space, then it's just a simple two-dimensional space. But then that's not very interesting. We want something that's more convoluted, and for that we add a particle. And a particle, well, the naive way to represent the particle is you have something, some structure overlaid on top of the space, and that when a rule is applied to it, that moves in some particular direction at a constant speed.
Okay, and so you have the particle and its momentum vector encoded?
Yes.
And so that's the red one, I guess. The red, or you have a hyperedge that has, it's a sequence of like the point and then the point and then its next point out.
Yes,
okay.
Exactly.
Okay. And then the orange one is just the point that has no momentum.
The orange one is a clock, but yes, that's that's actually a particle that's standing, but as we will see later, a clock is not, so this particular implementation of a clock doesn't really correspond to anything useful if you consider the requirements on it after special relativity, because no matter what you do to this clock, it is always going to be standing still, and actually, we should be able to do something to it, such that such that we pass to another reference frame, and it's an equivalent system, but the clock is now moving, and here it is not trivial how to do that.
But why do you have like so many edges between points in space? Like there's like 4 edges between neighborhood points.
Well, I think those are. Yeah, I don't know.
So that's just a hack for making the particle transverse correctly. So In one dimension, it's simpler, and you have just two edges, one in one direction and another in the opposite direction, so that it can travel both ways. And in two-dimensional space, if you just have that naively, then the particle will not be able to distinguish whether it wants to go to the left or straight ahead. And so that's why for higher dimensional examples, the rule is actually like this. So here, I don't just have the edges back and forth. I also have the hyper edges, which connect this vertex to this vertex. And they allow the particle to understand that this is actually a straight line. Well, that this is a straight line, as opposed to this. But it's really more of a technical detail of an implementation, and for the conceptual understanding, it doesn't matter that much.
Yeah, but
So
potentially there's like a simple way of doing it, because it's not immediately clear why you have to introduce such hacks, right? Because you already have a momentum vector. It's kind of, it has to already know where, comparing to underlying vectors on the space, kind of already know in relation where it has to, in which direction it has to move, right?
well, then to distinguish, so if the particle is currently here, then it has to know. So you have the momentum like edge and vector encoded here, and you know that the next base location of the particle is going to be here, because that's where the momentum vector is pointing. However, you do not know where the momentum vector should be pointing at the next iteration of time. And if you just take since we were working with subhypergraphs, if you just take the subhypergraph for these three vertices, it's going to be the same as the subhypergraph for these three vertices by default. And that's not something you want. You want to have an edge of.
Okay, I kind of get it. So there's not actually like a 4 arrows in there for binary edges. It's just there's actual hyper edge, so that you can need to get the 3 points, right? So that you can actually
you can see that here it's highlighted. But it's so that's not that important for the concept. It's basically the same as in one-dimensional space. And so if you take this system, which is the same particle, so it's here it's bigger. So it's the particle, it's the clock, and then the particle is moving to the left. Here we have a so since this edge is going right back to itself, then the particle is going to turn around, and then what is going to happen in the system is the particle will move to the edge, turn around, and come back. And here I have an even simpler subsystem that just simulates the last few iterations when the particle is already coming back. And so you see that the tip is in this direction. And so since the rule is we take the particle and we move it in the direction of the tip, what is happening in this system is we move it here, then we move it here, and then it collides with the clock. And so in general, in special relativity, simultaneity is not absolute, so it depends on the reference frame. So it's really hard to reason about that and to be able to confidently define that this system, there's something wrong with simultaneity there. But what we can speak about for sure is what is happening at one particular point. And with special relativity, there's a lot of really fun facts about it, including the one that we cannot actually measure the speed of light in one direction. We can only measure it for a round trip, and so we don't actually know. There is no experimental evidence contradicting the following statement: the speed of light is c/2 in that direction, and then light moves instantaneously in this direction. There's no way to experimentally check it, because if you send a photon there and back, what you're measuring is the round trip, and you can try all sorts of hacks with moving a clock to the other side. but then always you're going to have some little nuance that is going to mess up your experiment, and you will actually measuring the speed of light in a round trip. So the point is that measuring something in special relativity where you have something some things that are happening in different places is really, really hard. However, what is absolutely objective is what is happening, is the specific events that are happening in one place. So like we were discussing with James, if you have a car and there's a clock in the car and then the car hits a tree, if the clock is, if you have a clock somewhere outside, then you can argue about at which time the car hit the tree, but then if the clock stops when the car hits the tree and the clock is inside the car, then the clock necessarily stopped at some particular time, and that event should be the same in every, the time on the clock inside the car at the moment of collision should be the same in every reference frame, because otherwise you would just get completely unrelated evolutions in different branches of, in different reference frame. And in order for that to be absolute, what you need is the same events happening in the same place. So here, all of this is to say that here, when the particle finally collides with the clock, there cannot be any ambiguity as to what is the number of rings around the clock, which represent the time at the moment of collision. However, if we apply the definition of special relativity, of the Lorentz transformation from special relativity, then we are going to see that the number of edges around of these rings around the clock is actually less, because here we did this tilted slice as is required by Lorentz transformation. So this is the causal graph. We did the tilted slice, and after that the particle here has traveled one more, so one more event was applied to the particle in our initial state, which means that the chains of events for the particle and the clock were misaligned, and that allowed the particle to arrive to the clock sooner. And that is not at all what we want to happen. So here we can...
in more detail, can you show which event corresponds to what on this graph? Which one is actually a ticking clock where the particle is moving left?
Yeah, so in this chart, this is actually the clock, and this is the moving particle. It's slightly counterintuitive.
Yeah.
But basically, the idea is that here we have the rule that if you have just a ring around a vertex, then you at that time step make two rings out of that. And so at each step, so here we have one ring, here we have two rings, here we have four. Oh, I think that's already two here. So yeah, like 2, 4, 8, 16.
Okay.
So the mechanism for the ticking clock is if there's a one self loop by itself, there's another one added to it.
Yeah. So basically here we have this growth of the rings, and that's why the graph, so the nodes in the graphs, they are events that happen to a particular ring. And so since you have the number of the rings that's growing, you have a lot of different events, and they look like this. And then for the particle, you just move it, and so there's no, it's always just one event applied to the particle.
And there are two colloids because it spans over two vertices, right? It's because showing that there are two vertices out there.
Yeah, or maybe
two hyperedges.
The tokens in such a place, they are hyperedges. Yeah, and I guess also just for the sake of the people who are not that deep into the lore of the Wolfram models, we should talk a little bit about what the causal graph actually represents. So in the Wolfram model, it's a model of substitutions of sub-hypergraphs, or in a more general case, it's called set replace. So you replace some elements of a set by some rule, and once you have, so you can construct the one-way or the multi-way evolution of a certain system given its initial state and some rules, and so you just replace sub-hypergraphs with other sub-hypergraphs, and then after you have that evolution, you can construct a causal graph out of that. And here the nodes are not the same nodes as in the hypergraph, but they are the events of the replacement, and the edges in the causal graph are the causal connections between the different events. So if so each node is an event, and then if there is an edge between two events, it means that the same vertices or actually the same hyper edges participated in both of the events. And when we have the causal graph, when we basically when we draw it, the vertical dimension corresponds to time, because at each step you have the events that happened simultaneously in some reference frame, and then the horizontal axis tends to equate it to space in some sense, and therefore the causal graph is actually located in the Minkowski space. And for us to apply a Lorentz transformation to it, what we can do is again we just take in the original reference frame we slice it horizontally, and we say that the events that are at the same time in the original Minkowski space are simultaneous, and then when we want to apply a Lorentz boost, we take a tilted slice, and the events that happened here like this are considered simultaneous, and then we take this modified.
It's a bit confusing because you have the two simultaneous events, as you call it, but connected by a causal edge. So it's like they're time separated, right? So it's not really. So it's not very. It's not a correct slice, I think.
Well.
Like this one, right? Like
here,
this one is weird.
Yeah.
Because it's not like an actual anti-chain. Anti-chain would be like events like this. So there is no.
Can you inscribe? Can you draw on the Zoom so we can maybe see what you're pointing at? If you just keep your.
I'm doing it. I'm drawing it on Zoom.
Oh. Why can't I see it? Can you see it, Dugan?
I can see it.
Oh, you can see it. Oh, there, now it's coming up. Okay, got it.
Yeah. So in this particular example, the causal graph is too interconnected. So here you have this connection that is not supposed to be there, because indeed it would be it would be a causal connection between simultaneous events, which is not possible. But in general, that's the way you apply the Lorentz boosts. And so our initial state in the original reference frame was the state that's the state before any events were applied. And then if you want to get the state at time equals 1 in the original reference frame, we do it like this. Then time equals 2 is the next slice, and so on. And so this is the last slice. But then, and yeah. So this is time. and this is the space coordinate in the original system. And then if you want to transform to another reference frame, we say that for some moment of time, these events have happened, and these events have happened, and everything that's above has happened. And yeah, we forget about this college. And then we take that initial state, we apply the same rules to it, and then it transforms in a different way. And what we want to check is that the resulting evolution is the same as the original evolution, so that all the local events are the same, even though the simultaneity can be different.
Yeah, well, let me try to rephrase it so that we're on the same page essentially. So, well, first of all, this triangle grid-like causal graph is always annoying because technically it's always have only a single foliation. So you literally can't boost it or rotate it because it only has a unique foliation, right? So the fact that we always show an example of how it's like actually like tilt it a little bit, and it seems like you changed your reference frame somehow is always misleading. But anyway, so the point is that if you have one anti-chain or this slice of events, right, or right, and if you actually could change a different foliation and make a different slice at every taking every slice, you could have reconstructed the whole state back, right? So that's like the original, the main assumption that you have is like just taking a causal graph, and in its slice you can reconstruct the original state, which is the hypergraph in our case, right? So that's the main assumption, that you can reconstruct from the space-like separated set of events the whole state that we are operating on, right? So okay, so next thing what we do is you change the reference frame, right? And and pick another slice, and you try to reconstruct the state out of that new slice. And your claim is that this reconstruction should give you, after maybe some evolution of the original slice or other way around, you have to get the same slice, the same state back.
So it's not that you get the same state if you just apply if you just apply a natural foliation to the new to the transform system. So if you have okay, I guess it's easier to see on the example that I have later of a system. Yeah, so here this example is on cellular automata, but it's the same conceptually is the same, it's just easier to implement here. And here the original system is like this. You have a particle, you have again a clock, so here the blackness of the color is how much time has passed. And initially the way so in the Wolfram models, always what you start with is some initial state and a set of rules, and then you apply the rules, and you get a sequence of states, or the most general structure that you get for one-way evolution is the causal graph. And then in the causal graph, you can make some slices to get to a state. So, okay, let's draw this. So you take the Wolfram model of some state and some rules, and then you get this, the causal graph, and then what you actually want is to get not the causal graph, but something that is more pleasant to work with, which is the state. And for that, in the original reference frame, what you do is you just make slices like this, and then you say this is the state at time 4, and then the next state is going to be like this, and so on. However, that's just the original reference frame. What you can also do is you can take these tilted foliations, and just by taking the tilted slices and applying the events above the slices, you can already get a sequence of states that seem to be in a different reference frame. However, what you need is for that because the main thing is that all inertial reference frames should be indistinguishable. We should not have a privileged reference frame, and what you want for this sequence of states obtained from tilted foliations is for the rules to apply between these states too. So here, the way you obtained this sequence naively is not by applying the rules and the substitution system it's not by applying the substitution rules. It's just by applying the events that you got from another substitution system, and that is not how we describe fully as a system. What we want is some initial state and then applications of rules, and we should get the same events happening in both the original reference frame and in the transformed reference frame locally. And so what you do is you take one tilted slice, you obtain an initial state from that. You obtain some state, then you treat it as the initial state for the new system. And so here you can see that the clock actually became a particle because we transformed to another reference frame. And so here you can see that in that reference frame the clock is supposed to be moving and the particle is supposed to be standing. And so this is what you got. And here the way we get this system is just by applying the same rules as before, but to the new initial state.
The new state that you reconstructed from this tilted foliation.
The new state is reconstructed from one of the slices of the tilted foliation. Yes. Yeah. So here have you have here the bold slice, and you see that the events above the slice they have happened, and below the genuine, so you get some state, and you apply the same rules to it, and you get this beautiful evolution. But it is not given that will happen in any Wolfram model. And one of the things that would be nice is to have a way to check that computationally. And for that, we need a way to apply a Lorentz boost to that. And it's actually not easier to apply an arbitrary Lorentz boost. It's slightly easier for the cellular automata because there we have some strict definition of space because you just have the index of the cell. However, if you're talking about hypergraphs, this embedding is somewhat arbitrary in the sense that you cannot just confidently say, well, I took some embedding of the causal graph in the Minkowski spacetime, and then the Lorentz boost there didn't really work. So, your rules, they're not, they do not agree with special relativity, because maybe the correct embedding in spacetime is different. However, what is what is more strict is an infinitesimal Lorentz boost, because if you imagine a very, very small velocity in the Lorentz boost, then what you're going to have here is that some of the events from the next layer will go in the well, okay, so some of the events in the next layer are going to go in the slice, and some of the events will not. But then for these events, we're just going to have the events from the previous layer. So it just splits the state into two parts, to one of which we apply one more step. And then the question is, how do we do the split? And actually, the only condition we have is that the border between the two parts is a hyperplane. Because in the Lorentz boost, since this is a hyperplane, and these are hyperplanes, then, well, their intersection. So, okay, this is a hyperplane in the Minkowski space, and then we have the horizontal hyperplanes in the Minkowski space, which correspond to the original foliation, and then their intersection is going to be a hyperplane in the underlying space. So I don't know if this is completely clear, but just for a one-dimensional example, this would be just a simple split of the one-dimensional space into two, and then in general you can define a hyperplane by just taking 2 points, and then a hyperplane can be something that is equidistant between the 2 points, and then if the distance is less on one side, it's in one half. If the distance is greater on that side, then it's in another half, and then we can apply just one more step of evolution to one of the parts, and therefore we can apply the Lorentz boost, and we can check that this evolution can produce the same states as the previous evolution. So is that clear?
It seems like you're describing something like that in continuous Minkowski space, but you're only dealing with discrete events, right? So I don't understand how you can describe this hyperplane and like infinitesimal distances between them.
Well,
what is actually happening to events and slices?
So if you have something that's like grid, and then you apply, and then you have a hyperplane in the Minkowski space that is, flat in the continuous Minkowski space, and then you have an embedding of your graph in the Minkowski space, then the intersection, the grid is going to intersect with the continuous slice such that it is going to split the one of the layers into two. So a very, very thin, a very, very small, a Lorentz boost with a very, very small velocity. For that, a hyperplane is only going to penetrate one layer of events and not two. And the intersection of the hyperplane with the layer is going to be such that the events are just going to apply to one part of the state, with the parts of the state separated by a hyperplane. And you can define a hyperplane without embedding the state in some Euclidean space. You can do that just based on the graph metric.
Okay. A bit, I don't know, maybe an example would help, because I'm confused. It's like I understand that in the discrete setting, if you're given a causal graph and you have a like anti-chains or slices just following each other, right? You can kind of describe your boost, for example, that you just put one event from one slice to a different slice, if it's allowed, right? You kind of shuffle your events through between slices if there's no causal links between them.
We shouldn't think about series of slices. We should just think about one slice. So you just take the state for one slice. Okay, so I actually have this written down here. So here are some definitions. So a Wolfram model, it takes a state and some rules and it generates a causal graph. And then once you have the causal graph, which is sort of the ground truth of that system in a particular reference frame, then you can get the state. So we have two very different graphs here, the hypergraph and the causal graph. And the causal graph is just a normal graph where the nodes are the updates. And so you can get the state of the hypergraph from the causal graph if you pass in some slice. So the slices in the normal reference frame are parallel and horizontal in our embedding. And then the slices that correspond to another reference frame, they're not going to be that simple. And a way to apply an infinitesimal Lorentz boost, a way to get one of the states from the other reference frame is through this. And then once you have, so once you got the state in another reference frame, you can treat it as the initial state there, and you can apply the same rules to it that you would in the original reference frame.
Yeah. And it shouldn't change the causal graph, right? You're just gonna reproduce the same
might.
event.
No, it might.
That's the only thing I still don't understand. It's like if you just froze the causal graph, like at any slice, you just drop all the events below some causal graph slice of the causal graph. If you just drop them, in theory, you could just find all the current updates that can be possible, right? And just reproduce the whole future cone essentially, right? Because it's going to be the same. So because we are considering that it's like a single way causal graph, there's no like ambiguities. We just apply the updates how they happen, and there's always only a single way the update can happen.
So the counterexample to that statement is this. So here we took a tilted slice, and then we took it as the initial state, and in the tilted slice, since we applied, so yeah, this is a good example because here, have our simple one-dimensional space, and then this is kind of our space-time, and when we have, so if we apply an infinitesimal boost here, then it is going to split our system into two parts via some hyperplane. Okay.
Disco.
Yeah.
No, you activated the hyperplane. That was amazing.
That was great.
Yeah. So we split. Okay. We split our system into two parts using some hyperplane, and the hyperplane in this one-dimensional system is just going to be a very simple split of it into two parts. And so we are going to apply one more step of evolution to this. And if we apply one more step of evolution to this, then the particle is going to move one more step while the clock just stands still, which means it is going to arrive to the clock later. And in general, if they are separated by some distance, then it doesn't really, it doesn't raise any contradictions if the particle is suddenly closer to the clock. But then once they get together, the amount of event, the number of events applied to the clock should be, it should be coherent. The state of the clock should be coherent in some way with the state of the particle. And so here, the time that the clock displays when the particle reaches it is a very okay. That's an observable that should not be dependent on on who is measuring it, because that's just something that happens. And you can imagine that we have that we can have a rule that takes the particle and the clock, and then if there is at least 16 rings around the clock and there is a particle in the same place, then it does something special to it, like it destroys both of them. And then this is going to happen in this reference frame, but not in this.
All right.
All right. So the again, the entire point of the project is to narrow down which systems can work nicely with the rules of special relativity, and to brainstorm some particles. So we have the computational test that does a basic sanity check using a small Lorentzian boost, and I have applied it to a number of universes from the registry of notable universes, and 15 of them passed the test, and then 20 timed out. So, it's between 15 and 35% for the first 100 systems. And we should run the test with more resources and on a larger number of systems. And the more conceptually important chain of thought is what should the particles actually look like, because if we again look at what's happening in this system, the particle is actually not that big of a problem. It is just a photon. So if some particle, no matter what you do to it, no matter in which reference frame you are, if it always travels with the same speed, then it is just a photon, and it kind of makes sense that the simplest particle we can think of, it doesn't have any mass, and it's, it doesn't have anything going on inside it, so arguably it doesn't have an arguably time doesn't pass for it, so it makes sense for it to be a photon. But the clock here is a problem, because that's something that's standing, and no matter what you do to it, it is not going to move, whereas in general that should not be possible. If you have something that is standing, there's always a reference frame where it is moving.
There's
So
like it's like if you have a clock, right? It's not not a contradiction that there is a reference frame that measures a collision with a particle at a different proper time, or at a different time given that clock, right?
no, it
So
is a contradiction.
Not
If
obviously.
it's a real clock inside, well, if it's
But if you assume
an
that
object
you
inside,
changed your reference frame, it's like you're looking at this clock from some different perspective. It's not like you're sitting at the clock. If you sit at the clock, it's like you're not allowed to shift the perspective, and you're only updating yourself.
Exactly.
Well, it's not obvious to me why it has to be a contradiction.
So this is kind of a discussion. I don't know if at this point it makes sense to get into this, but a thought experiment might help clarify here whether this is a contradiction or not. And the experiment goes like this. If you're on Earth and you have a friend of yours that's in a rocket leaving Earth, and for them, because they're traveling faster than what you are, theoretically, time moves, slower or faster for them? Whichever way around it is, right? They have a different time dilation to what you have. So the argument is that if you have a clock on Earth, what your clock is saying is going to contradict theoretically, or objectively, what that person's clock is over there, if there's like a universal equivalence. But the way that this paradox resolves itself is for that person to come back to you, the clocks will then sync up again. It's not possible that that person, experiences time slower or faster and then comes back to you, and then you compare the clocks again, and the times are going to be different. So there's only a change in as far as there's separation, but to come back to the same point and compare the clocks in like a local environment, there will be no change in time again. So there's only a change.
No, actually,
change in speed.
no. Actually, so in your example, when the other clock comes back, the clocks are going to be different.
Well, that's the debate. That's what I wanted to ask. Maybe if
No, but that's the
Dugan-
it's siblings.
Twins.
Yeah, like
Yeah. Twin paradox.
you have two twins, and when the other twins return to Earth, she will be younger than the one who stayed on the Earth. But
Okay,
that's not.
Yeah. Mm-hmm. Oh, that's not
But
okay.
that is not. So the question is not whether the clocks are going to be misaligned when the other person comes back. It's so the statement here is that in every reference frame. So you can think of it in those terms, and then imagine the person on Earth has some sort of a clock, and then the other person comes back, and here the other person represented by the photon doesn't even have a clock. It doesn't matter, and she doesn't age, and it's just that doesn't really matter. What matters is the time on the clock of the first person when the other person comes back. When they're separated by some significant amount of space, it's hard to tell anything about their relative age or clocks or anything like that. But when they come back together, the claim is there should be some time on the clock at the moment when they come back together that is independent of the observer. So one example of this is so the other person comes back, and then there is a news article in the paper. The other person came back on August 13th of 2024, and then it's printed and all that stuff, and you cannot have it then in another reference frame. All the papers are going to actually say August 14th. It is there is an the substance of the events that happen in the universe is objective. Their simultaneity, simultaneity of events that are happening in different places is different in different reference frame. That's for sure, but that's not what we're talking about here. So here, you need to have some particular time at the clock when the other person comes back.
Right. So I guess like if someone's like riding on a skateboard and they have a clock on them, on their person, a dial clock, and they go by like an intersection, a particular intersection and you can see in their perspective, they hit the intersection at like, a certain time on their clock, 2:00, let's say. And if you're in a spaceship, like looking down at this event from a relativistic speed, you might see all that stuff happening faster. But in your view scope, you'll see that the clock that the person is wearing still, when they go by that thing, it's still going to be 2:00, and that's an invariant.
Exactly.
Okay.
Exactly.
Okay.
Yeah. There is an aspect to this. So what Steven actually says is that it can be different in different reference frames, but and so in some reference frames, if I understood him correctly, he says that in some branches, the causality can even be it's not like the causality can be violated. It's just that some information might travel with the speed of light. It's just that the probability of those branches is 0. So that is the claim that Stephen is making, and that is not the way I look at it here. So he looks at it through the prism of multi-way systems, and I look at it in a deterministic fashion, and I see, I look into what has to be true in order for special relativity to hold always. So that's one of the choices which can be seen as arbitrary, and then so in that
is it
sense,
is it maybe like in a way you're testing for some kind of laws of physics to be satisfied? It's like, yeah, maybe a causal graph gives you special relativity, but it maybe doesn't give you that the momentum energy has to be conserved. And in a way, maybe some systems like this example doesn't satisfy some of those conservation laws, and that's why everything breaks, right? With this specific choice of rules or initial condition or whatever. And here you just chose the universe that hasn't had some conservation laws satisfied. And that's essentially your search is for those kind of rules that have this condition, so that they have some.
my
Or is
search
it
is for
not the
the
wrong
for the
way?
universes. The question I am investigating is what kind of rules should we consider for the special relativity to always hold.
Mm-hmm.
And so if we are talking about energy and momentum, that's a separate question, and it's a separate condition, and then the same logic applies. So for instance, the transformations of energy and momentum under special relativity, they are derived for any reasonable rule, which is a very, very nice result. So if you transform space-time in this way, then and then you calculate the energy and momentum using the definition, then your energy and momentum are going to transform the way they're supposed to. And then for the conservation laws, they are not yet derived from the Wolfram model, and so it might turn out that they hold statistically because of at least for some subset of reasonable rules that have, for instance, the same amount of edges come into a vertex and come out of the vertex, but that's not really proven yet, and it's a speculation at this point. So I haven't yet talked about the particles, and again the clock we have there is problematic. So it's supposed to be like a standing particle, but it behaves like a particle that's always standing, which is not really physical because it should move in some reference frame, and that's why we introduce this fancy particle, which is the first one we've seen that can actually go at a speed that's lower than the speed of light, because constructing a photon is really easy. Constructing something that's not a photon is much harder. And so here it is not precisely on a hypergraph, although it can be implemented on one. And it was some so a particle that's moving with the speed c over 2 was implemented in the example with cellular automata. And this is what it looks like. So the idea is if you have something like the two very, very simple structures we have seen, the particle, the clock and the photon, it cannot generate a reasonable physical structure that is not a photon, because it has to move with different speeds in different reference frames. And for that, we have to be able to apply different rules in different reference frames. So if you have a rule that moves the particle, that it cannot always apply, because then the particle is always going to move the same way. So you have to have some rule for it to just stand. and for example, do something, and then if the particle is in the reference frame, in its own reference frame, that is, it is just going to stand still and tick, as we call this rule here. And then if it's moving, then it is going to move. And the way you do it is you don't have, you can, so the constraint we have is that we cannot just apply one single chain of events to the particle, because then if you slice it, so yeah, let me draw this.
I need to leave for another call quickly, but I look forward to watching the rest of this on the stream later. Okay.
Okay. Bye. Thank you. Yeah.
Oopsie.
Yeah, you were the host.
Are we still on stream?
Yeah, we're still live.
Okay, great. I'm just gonna leave my camera off and have this on in the background.
Okay.
Sorry about that. The hyperplane activation crashed the Zoom.
All right, we need to tell.
Yeah, I'm swapping back to come back on. There we go. Sorry about that, Lev. I think your hyperplane activation crashed the Zoom. No, I'm joking. That was my fault. Please continue.
Let's try to get that. It doesn't do it for me. All right. No hyperplanes for me.
I can do this.
All right. Lev, you're muted.
Right. Yeah. So if we imagine a causal graph that just looks like this, then however we slice it, it is always going to the particle is always going to have the same state in every reference frame, because you just say that the events that are here, they have happened, but the events that are here, they didn't, but it's still the same events. So what you actually want is you want several chains of events that are independent, such that when you slice it, you get a state that is different. So here, if in the original reference frame, the particle, the causal graph for the particle would be sliced like this, then in the transformed reference frame, it would be sliced like this, and the actual states of the particle are going to be different. So in this, with this particle, if you have here, imagine we have two numbers written in these cells, and we have a rule that takes a number and increments it. And so here we're going to have two chains that both increment their corresponding number. And then we have another rule that when the numbers are misaligned, the particle moves. And so here, when we're going to take a tilted slice, the numbers will start being misaligned. And so if you then take this state, then the particle is going to be like n plus 1. And it is going to start to move. And that is what I have implemented in the example of the cellular automata. So we have seen it earlier, but here you take a tilted slice, and then you can see that here you have both kinds of events, one is the tick where the particle is standing and the counters are incrementing, and then the other is move, where you take the particle that's here and you move it. And so here for the clock, which is just a standing particle, it is always the increments, and for the particle, it's the movement. And then when you take a tilted slice, you see that here this tick has happened for the clock, and this tick hasn't happened for the clock, so the clock starts being misaligned. And for the particle, it's the opposite. You have one more event happening for one part of the particle, but not for the other, which turns the particle into a clock and the clock into particle. And so, well, here the clock is defined as just something, as just a standing particle. And yeah, another nice thing about this is that you have you naturally have proper time here inside the particle that behaves in the way special relativity expects. So when the particle is standing, it's one tick per 1 unit of time, and then if the particle starts moving, then it ticks less often, so the proper time for the particle is slowed down, just like what we expect with special relativity. So is that clear?
Oh yes. Sorry, yeah, I was still thinking about the previous topic. Was kind of spaced out. But yeah, the slowing of times kind of makes sense. Yes.
Yeah. So this is one implementation of a particle, but what is bothering about this is that it's very arbitrary in this formalism, and the ideal answer to all of the questions of special relativity would be some natural formalism, maybe some way of creating hypergraph systems where everything behaves in a relativistically coherent way by default, and these structures, they are more natural. And one way of implementing these structures in a natural way is when you have a particle that's bigger and it has a bunch of different events happening chaotically inside the particle, and the events are not all causally connected. So they don't happen on the entire particle, they only happen to a part of the particle. And then if you have more events happen on one side, then the particle moves in that direction. So it sort of builds up momentum if you just apply the events, and if you have some imbalance, then it moves there. And so that's one way to implement in a way that is more in line with the chaotic systems you want to expect.
Mm-hmm. Yeah.
Yeah, it's interesting. So it's
really
like
confusing. It's like, go on, Dugan.
Right. So here you're trying to look at how to meter the speed of a particle moving across space. To have, stationary ones are just the ones that are like a self loop, and then other ones have a momentum vector attached to them so that they propagate along according to the rewrite rules of the hypergraph.
Yeah.
And so you have a space-like hypergraph, and then you have like this updating event acting on it. I guess something that I just think about is if you have a hypergraph which represents space-time itself, and you have all the particles moving at the speed of influence at the same rate, right? And the ones that are stationary just have their momentum vector pointed straight up in the time-like axis. And then the ones that are moving with a space-like component, have their velocity, their momentum vector tilted mostly towards the time axis, but a little bit towards the spatial axis. I mean, that's the kind of Minkowskian relativistic view of how everything moves. Everything is moving at the same rate through a space-time manifold, just in different directions. Some time-like, some space-like.
I tell
Well,
you, trying to like come up with a space-time picture. So instead of is it like somehow like 5-dimensional space-time you're describing? Because how do you actually move if you already have time explicitly defined in the hypergraph itself?
Yeah. So the thing with that statement is that yes, you can look at this momentum vector just from pure special relativity formalism, but the momentum vector in space-time, it's just an emergent phenomenon, because if you have it in the same way as if you imagine a way to make something like this but in space-time, then the big condition in it is that it cannot just be encoded in a simple way like this in the state, because if you just have a particle that's very simple and that only has one chain of events associated with it, then the particle is going to behave in the same way in all reference frames, because if you take a tilted relation, you're still going to be in the same chain of states of the particle, right? So here, if you take a look at this causal graph, this is the causal graph of the movement of the particle, and you can slice it in a tilted way, and you can slice it in a so you can have different tilt, you can have like whatever you want, but whatever you do, it is always going to be a state that looks like this, and then you take a state that looks like this, you apply the rules to it, and the particle proceeds to move with the same speed, which is fine for a photon, but not fine for anything else. And that's why here you need to have, for a real particle, you need to have a second chain of events that is independent of the first one. So that for that one, when you take a tilted slice, you have more events happen from one chain compared to the other chain, which leads to a different state and the particle that can behave differently.
Yeah. It's like if you just have two subsystems that you're describing, it's like they had some dynamics. It's like always, it's kind of clear that you can change the speed of updates of each of those systems independently. It's like, but it's kind of would correspond to changing the reference frame of that particular thing. It's like if you're speeding up your particle, it seems like you increase the velocity of that particular reference frame. So actually increase the particle velocity itself, right? So by itself, you kind of can't do it if you want to keep it fixed. But on the other hand, if you have a clock, you can also speed it up. But it is, in a sense, also has to correspond to just different reference frame or a different boost happening to that clock. So in a way to compare, all I'm saying is that in order to compare those two systems, it's like what's missing is like a third system that's like an observer that has to independently observe those things colliding without independently changing those reference frames of those systems, right? It's like, so you have to update the velocity, boost that observer instead of particle or the clock, right? That's what would correspond to the actual change reference frame and change. So that's not going to change the actual state. So that if without an observer you say that the clock is always ticks at the same moment of time when the particle overlaps over that clock, you have to change the third party in order to be consistent and coherent with that picture. But when you like change the velocity of a particle, like that you imagine that there's some kind of reference change and you essentially speeding up the particle, obviously it's gonna like arrive at the clock much faster because you essentially increased its speed. Maybe it's like it's incoherent in this way, so that actually in order to describe the system, you have to introduce some third party as an observer, and it's not obvious to me that it's not gonna be. You can't make it coherent in such a way that it always has to be like in order to act as an observable interact with both clock and the particle in such a way that you can't really speed it up, so that it's like multiple reference frame would produce different results. I don't know.
You have to be able to boost the particle just by picking which events have happened and which didn't. So for one, if you're talking about some, so what we want here is some framework of describing the particle. So a kind of systems on the hypergraph, or just in general in the Wolfram systems, and our main condition is that it should be okay. So the first condition is that it should be expressive enough for us to be able to encode the particle that is moving and the particle that is standing and all the speeds in between, and we should be able to transition between those different states just by picking different event different slices of events, and that is what allows us to do it here. So one way of trying to implement particles with the different speeds would be we take something like this, and then we can have the length of the tip correspond to the speed. So you might imagine a tip that goes all the way up to this vertex, and then the particle moves 2 steps at a time. Or you can have some intermediate state, which is something I also implemented, such that it takes the particle 2 rule applications to move to the next vertex. And then, in one case you double the speed, in another you half it. But then the problem with that is that you're still going to have the same speed in all the reference frames, which is not physical for something that's not supposed to be avoided. And here you have the option to apply more events here.
I'm still thinking what would happen if you actually have the explicit event of observation. It's like, why would it? It's like, obviously, it's like you said, if there is some rule that only triggers when your clock and particle overlaps, right? If that particular event, it's always going to be like a single event in the causal graph. Like if you just for example, if the actual particle gonna stop after moving to the left, it's always going to be in the causal graph. It's going to be a single event.
Yes, the observation event can be just a single moment.
Yeah, it's a single. In the causal graph would be a single thing, right? Like a single event of observation in the causal graph, and it's always going to be at the same position, and it's not going to depend on how you foliate the causal graph. Right, and so in a way, it's always going to be at the same distance away from the origin. So it's always going to be at the same number of events of clock ticking and the same number of events of particle moving.
No, but right? Okay. So again, if we come back to this example, here we can have the observation can happen at the moment where the particle is at the same place as the clock. And here, even though the observation is a single event, because the particle, or rather the clock, doesn't behave well, it can lead to different outcomes of observation.
Well, how? If there is just one event, right? Obviously, it's gonna. If you just run the system, right? It doesn't matter which order you update it. You don't reconstruct any states. You just update. If you actually reconstruct any state, any state from slice that goes through this observation, it's always going to be the same state because, right? Maybe it's going to be like a thing because maybe there's only one way to slice the causal graph that intersects that particular observation. Maybe you can pick some weird slices that doesn't involve this observation event and reconstruct the state that the particle moves through the clock at some different clock state, right? But it doesn't involve the observation event.
Well, I'm not talking about just different, just taking a causal graph and taking different slices. I'm talking about taking the initial causal graph, then taking a slice, treating the state we got as the initial state of the new system, and then applying the same rules to the updated system, to the other reference frame. And here it is not necessarily going to behave the same way as shown here.
I had a question about the hypergraphs you checked for. So you were looking at some of the Wolfram models, or the notable universes, or whatever. Can you scroll down to that?
Yeah. Yes. Yeah.
Okay, so you had these. So, what's happening here?
Yeah, so I take the split. I take the split via a hyperplane. So here there are some two vertices, and we consider the highlighted part is the one that is closer to one vertex rather than to another. And yeah.
So you evolve these, so these universes, they pop up from a starting condition, and then there's a rule that makes the space, and then you took that space as a static entity, and then made particles on it, and then
no. Here I do not consider particles, because in general it is hard to define what a particle is if you're just working with an arbitrary system. So if you here I just apply the Lorentz boost to the system without any additions like particles and so on. And I check whether the evolution after the Lorentz boost is the same as the one before.
Okay.
And so here, the way I apply the Lorentz boost is by splitting the universe, the toy universe, in the two parts, applying one more step to this one, and then that way we apply, that way we get the state after the tilted slice, which is our initial state for the new evolution, and we compare the two evolutions.
The evolutions in the causal graph, or in this itself.
Well, just the evolutions of the Wolfram model.
Oh, okay.
Yeah. So you take some state, you apply one more step to this, and then you that way you have a left state and the right state. You apply the same rules to both of them. You get two different chains of states, and you check that basically the same things happen in both chains.
Got it.
All right, I think.
All right. Yeah, I think
we should end here.
We should wrap it up.
Yeah.
Okay. Thanks for thank you so much for presenting. And,
thanks for inviting me.
Yeah, Nick, do you have any closing comments?
Are there any comments? Glimpse of Destruction asking something. Is there a sense of temperature? Maybe more edges depending on state.
The temperature would require multiple particles interacting at different speeds, and then you kind of, the particles make heat by motion. So I think if it's just one particle by itself at this point, there's not much of a notion of temperature.
You could also probably do something with entropy, and perhaps even just by looking at the causal graph. And also from energy and momentum, I guess you could just reconstruct something without actually defining what a particle is, but that's a separate and complicated project.
Right.
Okay, even energy, I don't necessarily like agree with energy being some flux of causal edges. It's like for me, energy is just some kind of potential of being rewritten, and also it's like an event itself. It's like the more there are events, right? They kind of represent the potential of the hypergraph being rewritten. So in a way, the energy stored in the hypergraph is how many events can be applied to that particular sub hypergraph. You know, it's like
Well,
how those events are knitted together by their dependency. It's not necessarily intuitively correspond to energy in any way.
you have disagreements with the mainstream Wolfram physics project. I have disagreements. If you're going to discuss all of them, the West Coast is going to miss dinner.
Yeah, fair enough.
All right. Thanks, Lev.